Back in section 2.1, we started talking about tangent lines and rates of change for functions. So I want to go back to that, and that was our motivation for talking about limits. And now we're actually going to go back to the idea of a tangent line and use the things that we've learned about limits in order to do that calculation. So think again about what you understand a tangent line to be. So if I want to think about what is the tangent line of this given curve at the point P that's shown here, how do I describe that tangent line? Hopefully you got somewhere along the lines of saying that the tangent line of this curve at the point P is the line that the curve looks like if you zoom way in to P. So imagining zooming way into that point, if you zoom in far enough, then that curve is going to start looking like a straight line. Basically, on the microscopic level, you don't see much curve to it. You kind of see it look pretty linear. And if you think about why we care about tangent lines, the tangent lines really describe the way that the function is changing at that point. So it's kind of like, again, at the microscopic level, with the given point that I've drawn here on this curve, I can say the function is increasing pretty steeply at the point P. And so it's the tangent line that really describes that increase, and specifically, the slope is a numerical value that we use to describe the steepness of a line. Okay, so how are we going to calculate the slope of a tangent line? We talked about this a little bit in section 2.1, which was a motivation for us talking about limits. The idea is that we are going to find some nearby point Q on the curve, and we're going to calculate the slope of a secant line through P and Q. Secant line is, just a line that cuts across 2 points on the curve. So it's going to be a line that goes through points P and Q, where P and Q are both on the curve. Calculate the slope of that secant line. And so we might say that the secant line has a slope of, we call it M sub PQ. And then what we're going to do is we're going to move that point Q closer and closer to P and calculate the limit of that secant line as, or the limit of the slope of that secant line as Q approaches P. All right, so let's take a look at seeing what this looks like in action. So in this case, we looked at this back in section 2.1 as an example, looking at calculating the slope of the tangent line to the curve y equals x squared at the point -2, 4. And what we did, and we had a little Desmos graph to show it, is we took a nearby point, with an input value of b. It's not going to seem very nearby, but I'm going to call this b. Now, the curve is defined by y equals x squared, so the coordinates of this point, the x coordinate is going to be b, and the y coordinate is going to be b squared. So if I was to call the first point P and the second point Q, then I could calculate the slope through P and Q is going to be b squared minus 4 divided by b minus -2. So it's the difference in y coordinates divided by the difference in x coordinates. And then the slope of the tangent line, I'm going to call that m sub t, is going to be the limit as b approaches -2 of that slope. So b squared minus 4 divided by, and that is b minus a -2 is b plus 2. So this is the limit as b goes to -2. Let's see. If I was to try direct substitution, you can see it's not going to work, and you should get that it will give you a 0 in the numerator and denominator. So there's a chance that this limit might exist. So I am going to mess with this rational function, and by factoring the numerator. So this is going to be b plus 2 times b minus 2 in the numerator, divided by b plus 2. And that is, the b plus 2's cancel out. And so this is the same thing as the limit as b approaches -2 of b minus 2. Now we can do it direct substitution. This is -4. And we did see in our exploration when we did this in section 2.1 that it appeared that the slope of the tangent line should be -4. So I'm going to now put that, and I can use the grid here and say -4 is going to be like this. I can go down 4 over 1. And that looks like a pretty good tangent line. Okay, so this is how we are going to calculate the slope of a tangent line in general. So here's the point -2, where the input value of -2. We take some nearby input point and then get the point corresponding to that input on the curve, and then we take a limit as that nearby point approaches our target input value. Okay, so this is what we do when we calculate the slope of a tangent line to the graph of a function f where at the point where x equals a. So this is my generic picture of a function y equals f of x. And what we're going to do is we're going to calculate the slope of a secant line, again, through the point a comma f of a and a nearby point b f of b. And then we're going to take a limit of that slope as b approaches a. So the slope of the tangent line, and that's going to be shown in orange here. And I'm labeling that as m sub t. So the slope of the tangent line is going to be the limit as b approaches a of the slope of the secant line. Or in other words, it's the limit as b approaches a of f of b minus f of a divided by b minus a. That is the change in the y coordinates divided by the change in the x coordinates. Okay, and so then what we have is a definition of the derivative of a function f at the input value of a is, it's the same thing. Like, instead of calling this moving point b, I'm calling it x. Okay, so if you look back here, that moving point here is b, and we take a limit as b approaches a of f of b minus f of a divided by b minus a, and in defining the derivative, I'm just calling that same number x. So it's the limit as x approaches a of f of x minus f of a divided by x minus a, provided the limit exists. And we call this the derivative of f at the point a. And we use this notation. There's a few different notations we'll use, but this is one notation that we use. You can say this as the derivative of f at the point a, or we also sometimes say, for shorthand, f prime of a. That little dash at the top is referred to as a prime. Sometimes people will call it f dash of a, but you'll most often hear me refer to it as f prime of a.